Julia? Daniel? Other Daniel?
Here.
Olivia?
Here.
Samantha? Julian? Claire? Allison? Lauren? Randall? Another Samantha? Brienne? Nicole? Cassandra? Annika? Christina? Dekis?
Here.
Alexandria? Annabelle? Mayan? Ariana? And Leah. Thank you. So what I want to do today is tie off 4-4. We got to effectively the last page of that section, and I asked you to read to the end of the section, and focus on the practice problems on the bottom of 197, which represent a pretty good test question because it summarizes how we represent, how we include energy in chemical reactions. And there are two ways, one of which we articulated in a lot of detail last class, which is called a thermochemical equation, whereby if you have an endothermic reaction, you include energy as if it were a reactant on the left-hand side of the arrow, even though we know energy is not a form of matter. And if you have an exothermic reaction, you include it on the right side as if it was being produced, as if it was a product. What some students find challenging is the fact that the kilojoules per mole, depending on what it's next to, sometimes confuses them. If you're given a chemical reaction and attached to it is kilojoules per mole, it means per the amounts indicated in that reaction. If it's simply next to a chemical species, you have to generate the balanced equation before you know how much energy to put there, okay? So that's what the practice problems on the bottom of the page are about. And look at what Sherry asks you to do. Given the following delta H values, none of which are attached to balanced chemical equations, write a balanced thermochemical equation and an equation using delta H notation with the smallest possible whole number coefficients for each of the following chemical changes. All chemical equations correctly balanced should be with integral coefficients. But you're not always given that based on the information you're provided. So if you look at the sample problem that Sherry gives you there at the top of the page, she discusses delta H and thermochemical. So delta H is easy. And at the top of the page, delta H notation requires the energy change to be specified along with the equation, but written separately. In other words, you write the balanced equation, and then to the right of it, you write delta H equals. And the delta H that you write, the sign is dictated by whether it's exo or endo. If it's an endothermic chemical change, delta H is positive. You don't need to put the positive sign in front of the energy, but it's positive. And you write that to the right of it. And once again, the kilojoules per mole represent that balanced equation that it's next to. If it's an exothermic chemical reaction, then delta H is simply negative. But the kilojoules per mole means the same thing in each of the contexts. In other words, next to a balanced equation. Okay? And if you look at what Sherry does here, the information she gives you, Same as the information she gives you in the sample problem, all right? The heat of decomposition of nitrogen dioxide is positive 33.9 kilojoules per mole. Now that isn't next to a balanced equation. And because of that, that means one of these. If it was next to a balanced equation, it would be per the amounts in the balanced equation. The point is, you gotta generate the balanced equation first. It's obviously endothermic, so if you decomposed 1 mole of nitrogen dioxide, and because it's a binary compound, if you decompose it, you're gonna get its elements. Nitrogen, which is diatomic, oxygen, which is diatomic. So every time a mole of NO2 is decomposed, you get half a mole of nitrogen and 1 mole of oxygen. But you can't leave that half there. But because that means one of these, when one of those is, when a mole of those is decomposed, then that is the amount of energy required. Now, that is not the finished thermochemical equation. It's just the amount required to decompose a mole of that. We have to make the coefficients integers, so we have to multiply everything by 2. So when we decompose 2 moles of NO2, then all of the coefficients now are whole numbers, and because we had to double the amount of NO2 we're decomposing, in the balanced thermochemical equation, we have to double the energy. And next to that balanced thermochemical equation, that means, that mole means when that amount of NO2 is decomposed, which is why we have to double the energy. And to turn it into delta H, we write the equation again, and to the right of it, now she doesn't have room there, but to the right of it, we would simply write delta H equals 67.8 kilojoules per mole. We don't have to put the positive sign in front of it. You can if you want to, but it's understood. Okay? So you don't write that or that and then write, oh yeah, delta H equals. You gotta write the whole thing again. So you gotta write 2 equations. 1 thermochemical, 1 delta H. And you have to do that for each of these. Now, what does that require? Well, it requires being able to predict products of a reaction given this little subscript here. In other words, what are the combustion of a hydrocarbon generator? What is the decomposition of a binary compound generator? This is formation, that means a synthesis reaction. You're making a compound from its elements. Okay? Now, if you haven't done those yet and checked your answers, you didn't do what I asked you to do. But that is a test question. It might not be those exact chemicals, but it will be a question like that. Thermochemical and delta H. So, do number 2. You're gonna need 2 separate equations. 1 thermochemical, 1 delta H notation. Start any time, folks. Number 2. elements are diatomic. So, to balance it, the least common multiple of 3 and 2 is 6, so 3 of these, 2 of those, 1 of those. The fact that we had to put a 2 in front of the ammonia means that in the thermochemical equation, we gotta write 46.1 times 2 on the reactant side. So, 92.2 kilojoules per mole plus 2 ammonia equals that. You could write the ammonia and the 90 plus 92.2 kilojoules per mole, it doesn't matter. You simply have to write it on the left-hand side because it's endothermic. And then for delta H, you write the same chemical reaction again. And then you write delta H equals positive 92.2 kilojoules. And that means when that much ammonia is decomposed to make that much nitrogen and that much hydrogen. Okay? So whatever you have to do to the reactant being reacted, whether it's burned or whether it's decomposed or whether it's there's single replacement involved, you have to, whatever coefficient ends up being in front of that is what you have to do to the energy term. Okay? Notice that C2H6 is CnH2n plus 2 and N is even. So when you burn ethane, you're going to need a 2 in front of that. You make carbon dioxide and water, so you're going to have to multiply that by 2. And in this case, because it's exothermic, the plus energy will be on the product side. In a thermochemical, there is no negative terms. You add energy to the left if it's endo, you add energy to the right if it's exo. But in delta H notation, written to the right, it's negative if it's exothermic, it's positive if it's endo, but the numbers remain the same. Okay? And I will let you do 1 and 3 and check your answers. It's not difficult if you understand what you're doing. Okay? And that represents the last set of practice problems in section 4.4. So, if you look at on page 199, number 2, convert the following delta H notation equations into thermochemical equations using the smallest whole number coefficient. So, there's a half there, so you have to multiply everything by 2. All we're doing here is condensing propane from gas to liquid. And because going from liquid to gas is always endo, condensing is exo, and that's why it's negative. So that's pretty straightforward. You're going to double that, you're going to double that, it's exothermic, so you're going to put plus 350 kilojoules per mole on the product side. Okay? And that's, all of those are exactly like them. Okay? Notice that a half or 3/2 both have to be modified to whole number. Okay? In number 3, she does the reverse. She gives you the thermochemical. And remember, if you add energy to the product side, it's exo, so the delta H notation would be negative. If you add energy to the reactant side, which it doesn't look, oh yeah, here we do in number C, so that would be delta H is positive. But again, whatever you have to do to the chemical species to make the coefficients whole numbers, you have to do the same to the energy. Okay? You don't necessarily have to do all of them, but you should be able to convert one to the other. Or, as the practice problems ask you to do, build both from scratch. And if you look on the next page, use the equations in question 3 to answer the following questions. So what was question 3? Well, you're given thermochemical, convert to delta H. Notice that every energy entry is a ratio. Kilojoules per mole. Okay? So if you know that, given the amount of a substance reacted, you should be able to determine the energy, either required or produced. If you're told the amount of energy required or produced, you should also be able to determine how much of the chemical species reacted. So let's pick one. How much energy would be released during the formation of 4 moles of methanol? So maybe it's unfair to know, expect you to know that methanol is CH3OH, but where is methanol here? Well, there's methanol. That's A. Okay? So, notice that that is not the way you want to write it, but because the coefficients aren't whole. But notice, because there's 1 mole of methanol in this, that tells you when you produce 1 mole of methanol, that's the amount of energy released. So you have all the information you need. How much energy would be released during the formation of 4 moles of methanol? Well, you have to go from amount of methanol to energy, because you're looking for energy, right? So before you put any numbers in, put the units together, just like we've been doing since September. You want to go from amount of methanol to energy. So moles of methanol is what you're given. You want to go to kilojoules. Not joules, because joules is too tiny. Well, if moles of methanol have to be converted to energy released, then that means moles of methanol have to go here. Look at the equation. You don't have to change anything. You don't have to multiply anything by 2. If you make 1 mole of methanol, 201 kilojoules is released, right? And what does she give you for sheet 1? Okay. So there's 804 kilojoules, or if you want, 8 times 10 to the 2 kilojoules. Nothing to it. Some is a little more nuanced than others. What about B? Now you're doing the other conversion. You're going from energy to amount. How many moles of nitrogen dioxide could be decomposed through the use of 168 kilojoules of energy? Well, if you go to D, notice once again that that equation tells you when 1 mole of NO2 is decomposed. Again, the coefficients are fractional, but that, because there's a 1 in front of NO2, and because the kilojoules per mole means that equation, that means when 1 mole of NO2 is decomposed, you require 56 kilojoules. So it's asking, if you got that much energy, how many moles of NO2 could be decomposed? Well, the conversion is just the opposite. You're going from energy to moles. the information still allows you to generate that conversion factor. So we're going from kilojoules to moles NO2, which means kilojoules has to do with it. How many kilojoules do you have available? 168. That equation tells you when 1 mole of NO2 is decomposed, it costs us 56 kilojoules. And it looks like we want 2, 6, 3, 7 answers. Yeah. That looks to me like what, 3? Any questions? It's not hard, is it? Number 5 is, if you're conscious, you should be able to get this. Does the following potential energy diagram represent endo or exo? Notice we went into it in way more detail than she does. All she's focusing on is final minus initial. And because delta H always equals potential energy of products minus potential energy of reactants, clearly delta H is positive here, right? Potential energy of products looks like, to me, like it's 450. Potential energy of the reactants looks like it's 300. So delta H, because it equals potential energy of products, final, minus potential energy of reactants, initial, which is what delta always represents, final minus initial. Potential energy of products here is 450. Potential energy of the reactants is 300. So delta H equals positive 50. Clearly endothermic. If we end with less stored energy than we start with, it's excellent. Where did that stored energy go? It was released into the environment, often as heat. The calculation's the same, except now this is less than this. So if the amount of stored energy has gone down, that's why delta H is negative. It's telling us the energy stored in what we have produced is less than the energy stored in what we started. So this is clearly exo. So we have 200. There's our potential energy of the products. 200 kilojoules per mole minus 250 kilojoules per mole. So delta H equals negative 50 kilojoules per mole. And she makes no mention of activation energy, activated complex, energy released when product bonds form. All she's focusing on is final minus initial. And to be honest, how you get from here to here has nothing to do with delta H. Okay? Doesn't matter what the activation energy is, high or low. All delta H depends on is final minus initial. Okay? The pathway taken to get there doesn't matter. And I mention that because if you take Chem 12 next year, whether or not I'm teaching it, I hope that whomever's discussing reaction kinetics informs you that there are ways to modify activation. And that's what a catalyst does, right? It doesn't change what we get, it doesn't change what we start with. It just changed how we get there. But because the only thing associated with delta H is final minus initial, the process getting there is irrelevant, right? Chemists have a name for that, they call it state function. So, that's 4-4. Now we begin what amounts to, in 2 sections, but probably mostly this one, what the majority of the arithmetic multi-step problem solving and the focus on units has been about. So we tie pretty much all the quantitative stuff we've been doing since Welcome to Chem 11, my name is Mr. Philith. We tie that together in 4.5 and 4.6, okay? Write a balanced equation for the reaction between chromium metal and hydrochloric acid to form chromium 3 chloride and a reactive gas. Now, if that question had been asked in section 4.2, if you look on page 175, you should need to be given the problem. Write a balanced equation for the reaction between chromium metal and hydrochloric acid. So, what type of reaction is it? Single replacement. What's replacing what? The elements of metal, correct? There's no metals in the thing it's reacting with, except hydrogen can be replaced by active metals if the hydrogen's in an acid. Why is she asking you that? Because she's reminding you need to remember this stuff. And to be honest, you shouldn't need this. That should be enough. So check your activity series, which is on page 175. Should this reaction proceed? Chromium is indeed above hydrogen. It won't replace hydrogen from water because it's not above magnesium, but it will replace it from an acid. So, metals are never diatomic, and they're all solids except mercury at room temperature. Hydroic means a binary acid, so there's hydrochloric acid. Now, why she gives you this is because chromium is multivalent. So you know you're going to produce a chromium something chloride, okay? And the most stable oxidation state of chromium is 3. And if you really wanted to get the specific, chloride is soluble with chromium. So that's aqueous. And because what's getting replaced is hydrogen, and because hydrogen is diatomic, there's your states. And then you simply have to balance it, okay? We got 3 chlorine here, we only got 1 there. But if we balance chlorine, we see we have 3 hydrogens and 2 hydrogens. So the least common multiple of 3 and 2 is 6. So if we put a 3 there, and a 2 there, a 6 there, it gives us 6 chlorine, 6 chlorine, 2 chromium, okay? Now, look at what she does in number 2. If 2 moles of chromium metal completely reacted in an excess quantity of hydrochloric acid. Now, why does she say that? That's what chemists often do. They often add an intentional excess of one chemical to guarantee that all of the other thing gets used up, okay? And the fact that we have more hydrochloric acid than we need means this isn't part of any chemical calculation we're doing, because we know we got too much of it. If 2 moles of chromium metal completely reacted, how many moles of hydrogen gas would be formed? Well, look at the balanced equation. Let's start from scratch. If 2 atoms of chromium react with excess hydrochloric acid, how many molecules of hydrogen can be formed? If 2 atoms of chromium reacted with excess hydrochloric acid, how many molecules of hydrogen would be formed? What's the coefficient in front of chromium?
2.
2. Okay. If 2 atoms of that react with more than enough of this, how many molecules of this can I make?
6. 6.
Molecules, not atoms, molecules.
3.
3. Is that a stretch, you guys? 2 atoms of this in excess this produces 3 of these. Doesn't that mean 2 atoms of that makes 3 molecules of this? What if 200 atoms of chromium reacted? How many molecules of hydrogen could I make?
300. 300.
300. What if 2 million chromium atoms reacted?
3 million.
How many molecules of hydrogen could I make?
3 million.
3 million. 2 jillion chromium atoms reacted, how many molecules of hydrogen could I make? 3 jillion, yay. If 2 moles of chromium reacted, how many moles of hydrogen could I make?
3 moles.
That's stoichiometry, you guys. The coefficients in a balanced equation are the mole ratios which govern reacting species. Okay? They are the axles. Remember the wheels we drew? What was at the center of each wheel? Moles. In a balanced equation, that is the glue that connects those 2 chemical species. Okay? Meaning, in this chemical equation, 2 moles of chromium equals 3 moles of hydrogen. Or you could phrase it the other way. If I made 3 moles of hydrogen, how many moles of chromium would I need? 2. And if I can say moles, I can say grams. I can say volume of a gas at STP. I can say volume of a solution if I know the concentration. Okay? All we're doing is using the coefficients of the balanced equation to connect chemical species A in a reaction to chemical species B. How many moles of hydrogen gas would be formed if 4 moles of chromium metal were completely reacted? Okay, well if 2 moles makes 3, how many would 4 moles make?
6.
Got any calculator?
6.
If 2 moles make 3 molecules, is 3 moles, then how many would 4 moles make? Wow. Maybe you do need your calculator. What's 2 times 2? Okay, if I double the amount of chromium, shouldn't I double the amount of hydrogen? Which is what? 6. Yeah. Is it too early in the morning, you guys? Oh my God. It's that simple. It's that simple. Okay? Look at what Sherry starts with. In the mole chapter, remember who wrote the mole chapter? Gary. In the mole chapter, stoichiometry was introduced through the quantitative relationship between the elements in the chemical compound. He called it compositional stoichiometry. No such term exists. Okay? This is Sherry's way of saying you never use that word for that, but you do use it for this. It is far more common to use stoichiometry to study the relationship between the various elements and compounds involved in chemical reactions. That's what we just did. Every time we say, if I have this much, how much of this can I make? Or if I need to make this much, how much of this will I need? That's stoichiometry. And the glue for all of those answers are the coefficients in the balanced equation, because those are the mole ratios. A balanced chemical equation, then, indicates the relative amounts of the chemicals involved in a reaction. And what's the SI unit for amounts? Moles. That's why they are the glue. And from the coefficients in the balanced equation, you generate the conversion factor. Remember, a conversion factor has to equal 1. So in this balanced equation, 2 moles of chromium equals 3 moles of hydrogen. 2 moles of chromium equals 6 moles of hydrochloric acid. 6 moles of hydrochloric acid equals 2 formula units of chromium 3-chloride. That's the only way you can compare chemical species A to B to C to D, through the coefficients in the balanced equation. Okay? Thus, for any chemical reaction, the balanced equation may be used to convert moles of reactants to moles of products or vice versa. It may also be used to convert moles of one reactant into another or one product into another. The key to these conversions, the key to stoichiometry, is the mole ratio, which is determined by the coefficients of the balanced equation. That is the heartbeat of stoichiometry. Okay? Once you have the balanced equation, you have all you need to equate any chemical species in that reaction to any other. So that's worth highlighting or underlining or isolating. Okay? That is stoichiometry. Everything we do over the next 2 sections is going to be based on it. You may find it helpful to review 2 wheel conversions introduced, that should say, in the mole chapter. In other words, there's the axle. What's at the center of each wheel? The moles. Where do those come from? In the balanced equation, those are the coefficients. Okay? All stoichiometry begins with the balanced equation. So, harken back to some of the things we've studied. If you're given names of reactants and asked to predict names of products, then you have to generate formulas. Obviously, if any of the formulas are incorrect, the balanced equation will be incorrect, if you can even balance it at all. And if the coefficients in the balanced equation are incorrect, you can't do stoichiometry. So in a very real sense, everything we've learned up till now is kind of crucial to moving forward. And not all sciences are like that, but chemistry is. So a student places 7.5 moles of chromium metal in an excess of concentrated hydrochloric acid. There's the balanced equation. How many moles of hydrogen gas are formed? Well, there's the balanced equation. How many moles of hydrogen gas are formed? We want to go moles of chromium to moles of hydrogen, right? Going to look pretty similar to the stuff we did way back in September. You want that unit to go away, it goes here. Get rid of this. Where do these come from? According to the balanced equation, 3 moles of hydrogen is produced from every 2 moles of chromium. How many moles of chromium do you start with? 7.50. Now, those are not sig figs, because you're counting. So those are exact numbers. So the mole ratio does not impact your sig fig. All right? Mole of chromium cancelled. 7.5 times 1.5. Retain 3 sig figs, 11.3 moles of hydrogen. Now, what if instead of moles hydrogen, she said what volume of hydrogen gas would be produced at STP? Well, that's not a big stretch, because we know STP means 22.4 liters per mole. So we could easily do that. Or how many grams of hydrogen? Or let's say we made this volume of hydrogen gas at STP. what mass of chromium would have been required? Well, volume of hydrogen would go to moles hydrogen. Moles hydrogen would go to moles chromium. Moles chromium, grams chromium. Nothing to it. Conversion from one species to another in a chemical reaction is accomplished by using the mole ratio between the two species. And again, therein lies stoichiometry. So all she's doing in all of these is doing moles to moles. But remember, because we know about moles, we know about other ways of representing amounts. Grams, volumes, okay? Volume of a pure substance, volume of a solution, all of that. How about 3? How many moles of calcium metal would be required to replace 1.86 moles of silver from a solution of silver nitrate? What do you need at the beginning of every stoichiometry calculation? What do you have to do first?
A balanced equation.
Balanced equation, because you need the coefficients of said equation to do stoichiometry. So that's a single replacement reaction. Calcium is way above silver, so you should be able to do that. You might even be able to include states. When I give you time in class to do this, or try it, do exactly that, okay? Because then you know when I'm here, if you're having trouble with it, rather than finding out for the first time when you're at home.
How is there 35 minutes left? It cannot be serious. Jeez, no, let's go. What am I doing?
Any nitrate solution is soluble, so. It should help the states. How many moles of calcium metal would be required to replace 1.86 moles of silver from a solution of silver nitrate? Well, that's a 1, that's a 2. So we're going from moles of silver to moles of calcium required. Pull it off, which means moles of silver goes here. There's 1.86 moles of silver was replaced. In other words, when all the silver and the reaction was over, and we measured the mass of the silver that was replaced, filtered it through the solution, dried it, weighed it, and converted it to moles, it would be 1.86 moles of silver. Balanced equation, that's a 1, that's a 2. 5 by 2, okay? And we'd want 3 sig figs, so that would be what, 0.930?
What?
And again, it's not a big stretch to think back to what we did back in chapter 3. Yeah.
For this sample problem, how come Sherry did the equation 3 times? Is it because there's 3 moles of hydrogen?
Which sample from?
Just the one on 202. So do we have to like show it 3 times, or like?
No, what she did is she's including, like, the first one, there's just the units. Second one, there's the numbers. So in other words, the mole ratio she put in the second step. And she put that in there because it's right next to what to think about.
Okay.
You don't have to do that.
Okay.
No, but she's just like, you're doing this for the first time. I mean, that's a fair question, but God, no, you don't want to write out 3
Okay.
times.
Okay.
Yeah, and then all she does at the end is do the arithmetic, right? And think of what we did, so how we set this up. Units first, numbers second, do the arithmetic. She's just separated it into 3 separate steps, but you don't have to write it out 3 times. No, okay? And if you wanted to go back to that wheel model, okay, you don't have to, but in terms of what might be coming, moles silver, moles calcium. You know, a lot that says we gotta marry ourselves just to moles. What if instead of moles silver produced, what if we had grams? How much calcium would it take to replace this many grams of silver ore? What mass of calcium would it take to replace that mass of silver? Grams to moles to moles to grams. Nothing to it. The only difference here is we're connecting it to chemical reactions. Okay? And all that, the tedium we went through, with all the diagrams and the units and the canceling, it was all about getting here, okay? Now, does that mean that every time you see a stoichiometry question, you gotta start drawing circles?
Yes.
No, that would be way too tedious, okay? But luckily, I have added an insert here to help with that, okay? It's kind of similar to the wheel model, except it's a little faster, okay? So let's say that what we just had on the board, we had moles silver, and we were gonna go to moles calcium, and we put grams to moles to moles to grams. What this is, it's sometimes called the molehill, is right underneath the balanced equation, which it doesn't really work to draw circles. But right underneath the balanced equation, it's like you're cutting little pie slices out of that wheel. The rest of the wheels are rounded. You draw a little pyramid underneath each of the chemical species involved in the question. And that makes it real easy. It makes it almost foolproof in terms of what you have to do. And remember, the hardest part of a multi-step calculation is what are the steps? What is my sequence? And this is a system that, you don't have to use it, just like you don't have to use wheels. But when you're doing this stuff for the first time, it makes it pretty straightforward. And I put that here. Another way to approach stoichiometry problem, it's not really another way, I think it's just a little more efficient than drawing the wheels. Okay? Instead of wheels, we're drawing little triangles, and we're affectionately calling them molehills, okay? Like you see in your backyard when the thing digs digs little trenches underground and comes up and this pile of dirt shows up. Here's another method of performing some types of basic stoichiometric calculations. It can be seen as a derivation of the wheel method discussed in the work text, but may prove somewhat more convenient to construct when solving these types of problems. Boy, that's written well, isn't it? At the end of the day, whatever method works and also makes the most sense to you is the one you should use. To introduce the method, let's begin with the typical mass to mole. In other words, given grams, want moles. So we're adding an extra step. How many moles of oxygen gas can be produced when 61.3 grams of potassium chlorate decomposes to produce potassium chloride and oxygen gas? Step one. The first step is always to write and balance the formula equation. Without that, you don't have coefficients. Without coefficients, you can't do stoichiometry. So there's the balance equation. Sometimes you're given the balance equation. And again, in a lot of Sherry's examples, as she scaffolds the stuff, she gives you a balance equation. But then eventually, she expects you to build your own. There's the balance equation. Now we read the question again. Step two. Under each substance involved in the calculation, in other words, I give information about this one, I want information about this one. Draw a molehill, which is simply a pyramid with the word mole on top. And again, you can see this as part of that wheel. It's just moles in the middle. It's just a little easier than drawing that wheel. And put it right underneath the chemical species involved in the calculation. So when we read the question, how many moles of oxygen gas? We need a molehill under oxygen gas. Can be produced when 61.3 grams of potassium chloride. That means that one goes there. We're not asked or given information about potassium chloride, so forget it. Don't worry about it. That's step two. And then remember, the only way to move from potassium chlorate to oxygen, or from any chemical species to another, is over the top of each hill. That is through moles. That's the axle, okay? Step three. Now you go back to the question again. You're given grams of potassium chlorate to solve the question. So place that unit at one of the unoccupied corners. You could put it here, or you could put it here, it doesn't matter. That's what you're given. That's what you have to end up with. But you can't go from grams of potassium chlorate to moles of oxygen. You first have to go to the top of the mole. Or if this was a wheel, you'd have to go from the rim to the center. Okay? That's step three. Step four. Now this may seem like, kind of onerous, all these steps, but after you've done these a couple times, the steps are easy. Using arrows, determine the calculation sequence, beginning in this case with what you're given, grams potassium chlorate, ending with moles oxygen. So remember all those arrows I've been drawing? And then eventually convert from the multiplication symbol, that's exactly what I'm putting here. So the point behind this is to get this. Step 5, write out the calculation sequence horizontally. You start with grams potassium chlorate. Step 1 is to moles potassium chlorate. According to your diagram, step 2 is to moles oxygen. There's your calculation sequence. Once you have that, the molehill has done its job. It's all about getting the calculation sequence. Write the calculation sequence from the molehills as a blueprint for the conversion steps. I bet you could take it from here. Replace arrows with multiplication symbols and insert appropriate denominators, meaning whatever was the numerator in the previous term, the only way it's gonna cancel is if it becomes the denominator in your conversion factor. So if we want that to cancel, it has to go here. If we want that to cancel, it has to go here. Whatever is in bold print is what that step is doing, okay? Notice no numbers yet. But now we put in numbers. What mass of potassium chlorate do we have? That's given. Where does that number come from? That's the molar mass from the periodic table. To make it simple, I've done it to 1 decimal place. Where does that come from? That's the coefficient from the balanced equation. And in the balanced equation, 3 moles of that equals 2 moles of this. As a final step, make sure the appropriate units cancel. The only unit you have left is the answer you want. Moles oxygen, do the arithmetic. Those are exact numbers. That's the 4 sig figs, that's the 3. So our answer should have 3. It's embarrassing, it's so easy. There's nothing to it. And again, there's no law that says I have to stop at moles oxygen. I could have asked for volume of oxygen at STP. That's just one more step. Or I could have asked for mass. One more step. Nothing to it. Okay? Now that was mass to moles. What about mass to mass? What mass of carbon dioxide can be produced when 319.4 grams of iron 3 oxide are reacted with excess carbon monoxide according to the following balanced equation? This reaction occurs in a blast furnace. When we dig iron ore out of the ground, it's usually this. We react at a high temperature with carbon monoxide. That takes the oxygen away from the iron 3 oxide, leaving so on. Okay? That's another redox reaction. So, generate the balanced equation. Well, it's given. You don't have to. It's done. Now we go to step 2. Construct the molehills. To construct the molehills, we've got to read the question again. What mass of carbon dioxide? Well, we're going to need a molehill here. Don't put the other units in yet. Just draw the pyramid with the word mole on top. Can be produced when 319.4 grams of iron 3 oxide are reacted. Well, you need a molehill here. You're given an amount of this. You want an amount of this. Now read it again to find out what other units are there. You're given grams of iron 3 oxide. You want to end up with grams of carbon dioxide. Once you have that, determine the calculation sequence. Grams to moles to moles to grams. 3 steps. Write that out horizontally. There's your 3 steps. Those arrows should be centered a little better. I hope they are in your book. Are they not? Good. So this is, there we go. My computer has nothing to do with mine. I was going to trash one of it. It's not your fault. Or this POS projector. I don't know. This was a prototype projector. This is the first projector in the school that they put in. I thought it was awesome, right? You mean a wireless? Oh my God. The guy that put it in decided not to put the cover on it. There's a cover that goes over it. Look at every other projector in the school. There's a cover over it. He left the cover over there for 6 months. And then one of the custodians threw it away. What is this piece of metal? Threw it away. And then the end of that year, which is like almost literally a year later, Mr. Olson said, "Oh, I should put a cover on that." There was, but the guy never put it on. And yet we paid him to install it without the cover. So I think sometimes, why did I mention that? This goes wonky probably more than any other projector in the school. Probably because it gets dirty. Probably because dust gets in there. I'm assuming the cover served a purpose. The guy that put it in didn't believe that, but yeah. You're not supposed to see all those wires because junk can get in there in the connection. Anyway, I digress. There's the calculation sequence. take it from here. That has to cancel, it goes here, that has to cancel, it goes there, that has to go here. Then put the numbers in. Where's 319.4 come from? We're given that. Mass to moles is always periodic table. Balanced equation. That's over the top of the molehill. That's the balanced equation, okay? So, going from here to here, that's the top of the molehill. That's what the coefficients are for. And that's molar mass. And then do the arithmetic. Make sure the units cancel. 264.1 grams. And, yeah, 4.6 phase, okay? Now, it could also have been what volume of carbon dioxide gas measured at STP could be produced. You could do that too, if you want. Nothing to it. I'm almost embarrassed it's so easy. And just when we thought it couldn't get any more fun. And this is something that Sherry saved till near the end of the session. We can also deal with questions involving volumes of molar solutions. In other words, I haven't given any examples of volumes yet. Volumes of molar solutions or volumes of gases measured at STP. Consider the following example in which one of the species involved in the calculation is present in solution. How many grams of copper will react to completely replace silver from 225 milliliters of a 0.100 molar solution of silver nitrate? Well, there's the balanced equation. How many grams of copper will react to completely replace silver? All the silver in 225 milliliters of a 0.100 molar solution of silver nitrate. So the quantity we're given is a volume of a solution. We're not given a mass of a reactant or a mass of a product. We're given the volume of a mixture. Okay? And in that mixture, 0.100 moles of silver nitrate exists per liter. And we're replacing the silver in that solution. Okay? Well, you might think, how do I do that? Well, let's just follow the steps. There's the balanced equation. Read the question again. How many grams of copper? Well, we need a molehill under copper. Will react to completely replace silver from 225 milliliters of a 0.1 molar solution of silver nitrate. We're not asked to predict the mass of silver. The chemical species we're given that has silver in it is the solution. The quantity we're given is a volume of that solution. So there's the two molehills. Now, read it again. What units are we given? What units do we want to end up with? We're given volume of a solution. We'll convert it to liters. And we want grams of copper. So in that volume of that solution, if we get all of that silver out, how many grams of copper will that take? And it's an interesting reaction to observe. Coil a copper wire and put it into a solution of colorless silver nitrate. Come back the next day, the solution's blue because copper 2 in solution is blue. And the silver are these nice crystals formed on this spiral copper wire. Okay? Next step, construct the arrows. We're given volume of the solution. Step 1 is to moles of the solute. Remember, it's the solute reacting, not the solution, the solute in the solution. Moles of silver nitrate to moles copper. Moles copper to grams copper. Put the correct units in. This has to cancel, it has to go here, that has to go there, that has to go there. Now put the numbers in. This chemical is a mixture in solution. That's the solute, that's what's reacting, but it's only available in that volume. So there's the quantity. If liters silver nitrate solution goes there and moles silver nitrate goes here, that's concentration. That's molarity. 0.100 moles of silver nitrate per liter of solution. That's balanced equation. That's periodic table. In the arithmetic, 0.714 grams of copper would be required to get all the silver out of that volume of that concentration. Now I say here, now try this method when solving some of the practice problems and review questions in this section. Decide if it works best for you. Well, there are lots of practice problems. There are lots of review questions. Let's use this method and try something from the top of page 213. Okay, we haven't done gas volumes yet. She gives you the balanced equation number 1. She gives you a balanced equation number 2. Oh yeah, this is, okay, let's, look at that. If you weren't given the products, did you write them? That's an ammonium salt reacting with the hydroxide. Remember, that's one of the double replacement where we get 3 products, right? Because when ammonium hydroxide forms, it decomposes into water and ammonia gas. That was the last double replacement type we talked about in section 4.2. Okay? How many liters of ammonia measured at STP are formed by combining a solution containing 40.5 grams of ammonium sulfate with a solution containing excess sodium hydroxide? I don't know why she put at STP down here. The ammonium hydroxide doesn't have to be at STP. So I think this is a misprint. Excess sodium hydroxide at STP. The solution, for God's sake. So, excess means it's not part of the calculation. You got too much, okay? Are we ever gonna do questions where we're given an amount of one and an amount of another? Yeah, but that's 4.6. For now, excess means that's not part of the calculation. So there's the balanced equation. How much time? We still have 10 minutes. That's plenty of time. So do that. Start, write the balanced equation. There's probably not, well, there's definitely not enough room to do it in your book. Write the balanced equation, read the question again, construct the molehills, read it again, put in the units, draw arrows, go from there. What I would do, she said unbalanced, so you gotta balance it. Temporarily write that as ammonium hydroxide, okay? So that ammonium goes with that hydroxide, temporarily write it like that, and then balance it as straight double replacement, okay? Makes it easy. 2 ammonium, 2 ammonium, 2 hydroxide, 2 sodium, 1 sulfate, 1 sulfate. Now pull the ammonium hydroxide apart into the same amount of ammonia gas and water. Remember we did that like a week or so ago? So let's write 2 water plus 2 ammonia gas. Okay? Now it's balanced. Now you guys take it from here.
What is ammonia?
My ass was not paying attention.
The fuck is ammonia?
Wait, is this just regular conversion?
Ammonium sulfate.
Fuck it. I'll figure it out later.
Boy.
nothing to it, you guys. I apologize in advance for the ease with which this material is now being presented. So, how many liters of ammonia at STP? Can be formed by combining a solution containing 40.5 grams of ammonium sulfate. Well, there's the solution. Now notice she doesn't give you volume of the solution and concentration. She gives you the mass of solute dissolved. But had she given you volume and concentration, you could do the same thing that we did with silver nitrate in the previous example. So, we read it again, we got mass of ammonium sulfate, and we want to produce liters and just.
Good morning, staff and students. As a faith and learning community, let us prepare ourselves for the morning prayer. In the name of the Father, Son, and the Holy Spirit. O God, we thank you for the life of Edmund Rice. He opened his heart to Christ, present in those oppressed by poverty and injustice. May we follow his example of faith and generosity. Grant us the courage and compassion of Edmund as we seek to live lives of love and service. We ask this through Christ our Lord. Amen. St. Thomas More, Blessed Edmund Rice, live Jesus in our hearts. In the name of the Father, the Son, and the Holy Spirit. Amen.
So, you got enough to actually finish this section. Look at number 3. Zinc arsenate. What the hell? What's that ion? Well, where's arsenic in the table? Right underneath phosphorus and nitrogen, right? What's the charge on a nitride anion? It needs 3 electrons, right? Arsenic needs 3 electrons. So it's going to be 3 minus. You get that? Nothing. It's easy. Okay? So, I'd like you to... Thursday we have a late start, right? And Friday, why are we having mass? What mass is for Friday? What's that for? There's like a feast day in January or something? With what moon?